Okay, so orthogonal basis of subspaces. I just decided just to redo this because just in case we rushed it in the class. So going back to orthogonal vectors, right? So just a quick reminder what orthogonal vectors are. And orthogonal vectors are two orthogonal vectors if their dot product equals 0, right, of two different vectors. So that was our brief introduction way back in the day, even into multivariable calculus. You saw that before in a little bit. We'll get much more in advance of what this represents in this section here. So first definition is let S be a set of vectors in Rn. Then the set S is said to be orthogonal set if each pair of distinct vectors in S is orthogonal to each other. In other words, I have to, if every combination of the dot product of these vectors give you 0, that's what's called an orthogonal set. Okay. So because of that, we have this main theorem. Again, let S be the set of vectors, be non-zero in Rn, and if S is an orthogonal set of vectors, therefore S is a linear independent set of vectors. Okay. Which means if it's linear independent set, we automatically know it's going to be a basis, and that's going to be our next definition here. So let W be a subspace over N, and let B be these vectors, be a basis for W, and if B, this basis, is orthogonal set of all vectors, basically this is happening. Well, if they're orthogonal, therefore, again, linear independent, therefore by default, this is called an orthogonal basis for W. Okay. And we'll talk about orthonormal later on. That's the one thing I think I didn't do much in class, is basically everything is scaled down to just a length of 1. We'll talk about that much more and how to get an orthogonal vector as well, or orthogonal basis of any kind. Okay. But for now is, well, if they're just orthogonal to each other, we have a subspace that's also orthogonal, or it's called the orthogonal set. Okay. So really quickly, we're going to show if this is a orthogonal set or not. So all we have to do is just do the dot product of each one individually, and we could tell. So this gives me 1 plus 0 minus 1 plus 0. So that works. But again, just because one worked doesn't mean all of them work. So if we just do this with this one, I get 1, negative 2, positive 2, and 0, which gives you 1. So that doesn't work. Right? It doesn't give you 0, so this would be a no. Okay. Now the next part is actually pretty interesting. Show that this is not a subset. So the three situations is, right, easily just show that this is not in S itself. So the 0 vector. And remember, this is a set of vectors, so these are the only ones I can use. There's no arbitrary values, so there's no way I can add these together to give you 0, 0, 0. Because let's say, for example, if I do V1 minus V2, right, well, the first one gives you 0. However, I have to have V3 somewhere, and if I just add it, then that gives me 1 on top, not 0. So we know that already the 0 vector is not in there, so this is also a hard no off of that. Okay. All right, so when do they actually work out? So show that the set of vectors is orthogonal. So all we have to do is show all arbitrary combinations. So this gives me 3, negative 2, negative 1, 0. I'll do the other one. So it gives me 1, negative 8, 7, 0, and the last combination. Just that one. So it gives me 3, positive 4, and negative 7. Check. So this is a orthogonal basis in R3. All right, so because of that, we have the corollary. Now we're going to talk about something called orthonormal bases. Okay. This coordinate, again, kind of weird. Let W be a subspace in Rn, where the dimension of W is P, and if S is an orthogonal basis, or orthogonal set of P vectors, therefore, again, S is orthogonal basis. Again, this is a weird corollary based off that. It's just, in other words, this is going to be the dimensions of the orthogonal basis. You know, I'm not really sure why they needed it, but, you know, hey, each of those basically is the basis going to be P itself. Yeah. Right, but this is where I want to go by orthonormal basis itself. Okay. The only difference between orthogonal and orthonormal is all we're doing is scaling everything down to a length of 1. So we're just shrinking the entire vectors down. Okay. So what this means is we're already starting with an orthogonal basis, and then we're just scaling it down using its normality. Okay. Or in other words, just making a magnitude of just length 1. Okay. And it's pretty straightforward. Again, we talked about this before. The length of the vector is just dot product of its transpose in the square root, and we multiply by its original vector to begin with. Okay. So, for example, given an orthogonal basis, we want to find an orthonormal basis, so we just got to normalize all of the vectors. So it's basically just the dot product of each vector put together inside the square root. So it's going to be 1 squared plus 2 squared plus 1 squared is the square root of 6. So we say, we'll call it B, U1, I call it, is equal to 1 over the square root of 6, 1, 2, 1. Same thing applies here. So 3 squared is 9, plus negative 1 squared is 1, plus negative 1 squared is 1. So this is the square root of 11. So U2 would be 1 over square root of 11 times the vector. And then find the last one, the 1 squared, 4 squared, and 7 squared. So there's a grand total of 66. There we go. So we normalized each individual vector. Okay. Now, this is a very interesting concept to finish up this part, like S in the middle of this section, is finding a solution with a basis. Okay. So remember, linear algebra is solving for a system of equations, right? So we did all this basis, subbases, and all that. You know, what is it useful for when it comes to solving for a system? And now that we have a little bit of foundation, where does basis comes to play? Okay. So if we have a basis of a subspace W in Rn, so this is automatically a basis, then any vector in W, so pick another vector, call it V in W, that means V is a linear combination of all the other vectors in W, because it's a basis, right? It's a foundation for it. So in other words, this is true, where W1 all the way to WP is the actual basis of this subspace. Okay? And this A1, A2, A3, or A4, or arbitrary like X1, X2, X3, are the coefficients that make this actually work, right? So pretty much I summarize what I talked about here. But these letters are actually pretty important. So this A1, A2, A3, all the way to AP are called the coordinates of V with respect to the basis W. So it's a big old mouthful. Okay? In layman's terms, is again, they're just the coefficients of vector V using the basis B. Basically just the coordinates, right? Or the coefficients in front of it. Okay. Which is pretty interesting because now we can actually find those coordinates based off this basis stuff. So let's try this out. So given a basis with the vectors U1, U2, U3, and a vector V, find the coordinates of V with respect to the basis B. So again, this is basically asking to that, right? Or nothing's really changed, right? Because according to my equation, this is exactly right. These W's 1, 2, 3, 4 is the basic, if you want, the actual matrix A, and these coefficients you can call them like X, the vector, equals V, right? It's the same process. So again, we're calling it something different. We're using different ways of describing it, but it's nothing really brand new. It's the same old stuff we've been doing over and over and over again itself. So really, putting these together, all I want to show is, given this matrix with all of these vectors in it, when is this equal to 5, -5, -2? And then we just solve it accordingly. So I'll quickly go over it. So add these two together. So row 2 plus row 3. And I'll do the same thing. So I'll just add row 3 plus row 1 together. You notice we're pretty much already done with one of the rows. That's kind of nice. So I'll just divide by 3. Okay. So I can use this to get rid of these ones here. I'll just do negative row 1 plus row 3. Yep. And then just pop a negative and just add it to row 3. And we're pretty much almost done there. Okay. So now I just divide this by 3 and just get rid of that. And eventually we get our nice unique solution, which should always work, right? Because there's always a linear combination, so you should always get an actual answer. So we get, converting this goes down, this becomes -2, nope, just 2. Yeah, -2 and 1. So what does this mean, right? So this is mean A1 is 1, A2 is -2, and A3 is 1. So if I go backwards, we could say vector V is equal to 1 times U1 minus 2 times U2 plus 1 times U3. Like that. And again, this is kind of nice because you're guaranteed to work because it has to be a linear combination as long as we have already a basis. Okay, so this is an interesting way, right, when it comes to its, linear combinations. Now, we also talk about orthogonal, right? Why is orthogonal pretty important, just besides just being a basis? And because technically, I'm depending on how you are, there's an alternative way to find this, or in other words, finding that. However, there's a drawback for this. This alternative form only works if you already have an orthogonal basis. That's the key thing. Okay. There's a lot of manipulation when it came to it, but I'd rather just give you guys the actual formulas because there's no point in going over the actual how to do it. So given an orthogonal basis in R3, and we'll just go in R3 because in R2 you could just drop them down 1 degree. Okay. And a vector V. So therefore the actual values A1, A2, and 3 are broken down into these type of situations. And it keeps going into continuous, right? Like A4 will be following the same pattern as this one. They will use W4, V, W4, W4, right? And it keeps going in continuous fashion, right? So like A sub n would be W n transpose V over Wn transpose times Wn. Right, that would be like arbitrary nth value if we go to like, in Rn itself. Okay. But again, there's a drawback. We first have to actually know it's an orthogonal basis. Okay. So I made a mistake, but let's suppose this actually is an orthogonal, and it actually is orthogonal. I just forgot to write it in the example. So find the coordinates of B with respect to the orthogonal basis B with the vectors W1, and these should not be there, W1, W2, and W3, and with this respective B. Okay. So this is going to be process here. So it's this dot product that. Let's just first start doing that. So that times that gives you 12, negative 6, positive 6. So just 12 on top. So this is going to be 12 divided by the transpose of itself. So 1, 4, 1 gives you 6. So A1 would be the division of 12 divided by 6, which just gives you 2. And you do that for the rest of them going down. So for next one, you just, it's literally the same equation, just use the second vector instead, right? So let's skip this step here. So 33 divided by 11 gives you 3. And then finally the last one. I believe. And then this transpose, 12 times 12 is 144. That's a big number. Oh no, what am I doing? Not this one. This one. 1 times 1 is 1, plus 16, plus 49, which also gives you 66. So A3 would be also 1. There we go. So again, this is an alternative to do it, but this, again, only works if we're given already an orthogonal basis. That's kind of a bit of a drawback. But the question is, I guess this is not that bad, right? You don't have to do matrix conversion to do so. It's just a simple equation, right? So I guess it's kind of easier, but again, the drawback is, well, not everything is orthogonal basis, right? Well, the question that becomes, well, how do I get one? And that is not as fun as you may think. So that's because the last theorem of the section is the Graham-Smith theorem. So this says let W be a p-dimensional subspace of Rn, and let the vectors be a basis for W. Then the set of vectors used is orthogonal basis, meaning I could convert any basis I want to an orthogonal basis by following this template. Okay. So now, given a basis, I can make it orthogonal, and then from there, I can just use the last theorem. Sometimes you don't really want to, but hey, to each their own, right, when it comes to it. But again, this is how we make any basis orthogonal to each other. So this process, again, looks horrible and a little messy. This is the nth term or ith term itself, right? Now the good thing is, when it comes to this portion, the first vector is automatically the first vector being orthogonal. Okay, so no matter what it is, we have at least one down. Okay, now to get the second vector, we do W2, so the second vector minus this bad boy right here. Okay, which is notice is about the same process of what we just did here when it comes to that equation. Okay, so it kind of mimics it, so it kind of makes sense, right, how to get those. Okay, and then unfortunately it follows a chain after that. So first we start with 1, Then 2, you subtract the second minus this. So therefore, to find 3, you're actually doing 2 subtractions. You do W3 minus, technically, the first and the second. This is like U1. So this is U1 and U2. So therefore, if it's U4, you do W4 minus 1, minus 2, minus 3. And in general, we have this happening here. Right, where this is all the sums. So if you want, you could just factor out the negative, add these sums together, and then just subtract at the very end, which is probably, I guess, depending on the approach itself, right, what you do. But again, you know, at this point, R3 is usually what we're going to stop at anyways. Okay. So let's try using this Gram-Schmidt equation here. So generate an orthogonal basis for this vector here. All right, so it is already orthogonal, which is great. That's the good part. But let's just check, you know, when it comes to it. All right. All right, so first one is nice. It's always given to us. So U1 is just going to be the vector 1, 1, 2. Check. Good. So it's just an R2, right, which is nice. So therefore, we're just going to go up to here. 2 vectors in R3. Well, technically R3, but 2 vectors in R3. Okay. So to get U2 is going to be W2. Okay. Now this is going to work for. We got to first transpose and do the dot product individually, and then finally multiply it by the original one here. Okay. All right, so just let's do transpose. So it's going to be this transpose times that. Okay. So it gives you 0 plus 2 minus 8. That's looking like negative 6. So this fraction is going to look like negative 6 over something. And now I just use transpose, U transpose. Basically just transpose or make the dot product of this vector. Okay, so that's just going to be, I'll put it here. So I already have it. So 1 plus 1 plus 4 gives you 6. That's nice. So 6. And then times the original U. Like that. So this ends up being negative, 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 positive. So it's just a positive 1, so I'm just adding all this together. So this is my U2. So my orthogonal basis are the vectors 1, 1, 2, and 1, 3, negative 2. Okay. So let's just go up one more vector and one more degree here. Now we're on 4 with 3 vectors. Okay. All right, well, the good thing is the first one's the same. All right, so to find U2 is going to be an exact copy which I did above. So U2 will be this, or sorry, no, not U2, W2, so this one here, 0, 1, 3, 1, minus. All right, according to the equation like we did above, it's going to be U transpose times W2. All right, so this with this. Okay, so that gives you 0 plus 1 plus 6 plus 1, it looks like. So it looks like 8. So 8 on top. And then I transpose itself. So basically this transpose itself. So that's going to give you 0 plus 1 plus 4 plus 1. So a total of 6 looks like. And then again, according to the equation, U1. All right. So I'll simplify this a little bit. This is going to be 4/3. So minus 0, 4/3, 8/3, and 4/3. So therefore U2 is equal to 0, negative 1/3, 9/3, so 1/3, and negative 1/3. Okay, so then to find the last one is just going to be follow this format. So W3 minus the transpose of now U2 with W3. So it's going to be this one with this one. Okay. Divided by this transpose itself. So this fraction with this fraction, and then times this one. Like that. And eventually you get this. There we go. So those are our orthogonal bases. Good stuff, good stuff.